Hello everyone, welcome to today's lecture. In this lecture, we'll discuss about the introduction of moment of inertia and we'll try to see what moment of inertia is. And before going there, we'll discuss about some similarity of linear motion and the rotational motion, and then we'll continue to the topic of moment of inertia. Now let's start. Now see, in linear motion, there is force. In rotational motion, there is torque. In linear motion, there is velocity. In rotational motion, there is angular velocity. In linear motion, there is acceleration A. In the rotational motion, there is also acceleration, but it is angular acceleration. And also, the displacement is here for the linear motion, and here the angular displacement, that is the angle only, theta. So right now, suppose one mass is there, which is free to slide, which is free to go anywhere. I am applying one force in a linear motion case. What will happen to this mass? This mass will get some acceleration. So acceleration we can get by dividing the force by the mass, or you can call it inertia also. And similarly, in a similar diagram, if I want to draw, suppose one mass is there m, and it is connected from a pivot point with a massless rod. This is a massless rod, and I am applying one torque. So if this is x-axis, this is y-axis, I am applying one torque like this. So what will happen? As I told that if we apply force in a mass, it will get acceleration. If we apply torque in this mass system, it will get angular acceleration. So angular acceleration, we can write T. In linear motion, we divide force by mass. So in rotational motion, a similar case, we will divide the torque by the mass, or can we call it rotational mass? That is not similar to mass, but it is rotational mass. Some rotational inertial property is there, rotational mass. If we divide the torque, we will get the acceleration or angular acceleration. Now, by dimensional analysis, we can find out what is actually the rotational mass is representing. What is the dimension of this alpha? Dimension of this alpha is radian per second square. So, radian has no dimension. So, it is only per second square, 1 by second square we can write. T to the power minus 2 we can write. What is the dimension of torque here? Torque is represented as Newton into meter. There is multiplication of distance with the force. So, it's Newton into meter. So, Newton means kg meter per second square into meter. So, it is kg meter square per second square. So, we can write the dimension of torque is m L square to the power minus 2. Now from this, what will be the rotational mass dimension? You can write it here, rotational mass dimension. Dimension of torque divided with the dimension of alpha, or the angular acceleration. So m L square to the power minus 2 by t to the power minus 2. So the dimension is m into L square. See, so it is kind of kg into meter square we can tell. So see, in the linear case, it is only kg. If we divide the force by the mass, that is kg, we will get the acceleration. In the rotational case, if we apply torque, we have to divide the torque by not only this mass, but see, with mass, meter square is also multiplied. So there is some rotational property this entire system is having, which is not only mass, but this property is also dependent upon the distance from the axis. What is this meter square? This is the distance from the axis of rotation. So this is rotating with respect to this point. So this distance square is basically the distance of this mass from the pivot point or the rotational point. Now let us understand it in a better way. So we got to know that rotational mass is also kind of rotational inertial property. Rotational inertial property. Inertia we can take. That is not only the kg, but the unit is kg into meter square. So this is also called, this rotational property or rotational inertia of a rotating body is also called moment of inertia. Moment of inertia. So we are going to discuss about this moment of inertia in this lecture. Now what is moment of inertia? As I told that suppose one mass M is there, it is connected with this pivot point or the center point of the rotation with a massless rod. If I am going to apply some torque, it will get some angular acceleration, and this length of this massless rod is L. Now see, the dimension of rotational inertia or the moment of inertia is kg into meter square. So what is that kg into meter square? It is denoted by I, moment of inertia. That is mass into the distance square from the pivot point. So it is m into L square in this case. And see, if we define axis like this, x and y axis like this, then z axis is outward. We'll denote it by a circle, dot the center as z axis, the outward. So this is rotating in this direction. A torque is applied in this direction, so it will rotate in this direction only. So this system will only be able to rotate with respect to the z axis. So it is also called Iz. So Iz is m into L square in this case. Now what will happen if I join another mass with a massless rod of the same length L? Then the torque I am applying T. So it is only able to rotate with respect to the z axis. So then Iz, or the moment of inertia with respect to the z axis, that will be, so for this mass it is located at distance L from the center of rotation. So we can write m into L square. But this mass is also attached with a massless rigid body. So this mass is located at how much distance from this center of rotation? L plus L, 2L. So plus m into 2L square. That will be the moment of inertia with respect to this axis. So it is basically 5 into ml square, Iz. Now if I tell that, okay, I am applying T amount of torque in this direction. So T is basically, I am writing T into k cap. Because it is a vector quantity, I can write T into k cap. What is the amount of angular acceleration this system will get? So very simple, alpha will be, just like we divide force by mass in the case of linear motion, we will just divide the torque by the rotational mass, that is the moment of inertia. So it is Iz. And it will get in which direction? This direction, Z. So it will always be K, so it is a vector. So it is T by 5ml square into k cap. That is going to be the angular acceleration of this system. Now let us discuss some more examples of moment of inertia. This is a center point. Two M masses are attached through two massless rigid bodies with the center, and I am trying to rotate this entire body like this. This x-axis, this y-axis, so z-axis is this one, outward. So this is rotating like this, trying to rotate like this. What will be the moment of inertia? Because this is rotating with respect to z axis. So Iz you have to find out. It's very simple. If the length is L, M mass is located at L distance from the center. So Iz will be the summation of all the masses into that distance square. So ml square plus this mass is also at distance L. So you can add. So it is 2 ml square Iz. Now if I give you this system, M, all are attached with massless rods. So only point masses are there. So what will be the moment of inertia in this case? See, we have to take summation of all these masses into the respective distances square. So all the mass into the respective distances square from the axis. I equal to 1 to n. That is the moment of inertia. So here in this case, all m masses are at L distance from the center of rotation or the axis of rotation like this. So it will be summation of all the masses into the distance square. ml square plus ml square plus ml square. So it will be 4 into ml square. That is the Iz. Now this is all about point masses. All the masses are point masses, so you are easily able to find out what is the distance square, and you are just multiplying the mass with that distance square, then you are getting the moment of inertia. Now what happens to distributed masses? So in general or in real life, we do not encounter this kind of scenarios. Often we encounter, suppose I am trying to rotate a rod of mass m. What will happen to that? Now I am telling that this rod is not massless, rather this rod is having mass m and the length is L. And similarly x and y axis is kept like this, so z axis is outward. Now it is trying to rotate with respect to z axis. You have to find out the moment of inertia with respect to z axis. So Iz you have to find out. Now before going there, I will just give a brief about what happens if only one particle is not in the system, rather there are multiple particles. As I told in the last minute that this all masses constitute one system. All these masses are located at different distance from the axis of rotation. Let's say this is the axis of rotation, this is the x-axis, this is the y-axis. All the masses are located at different distance. M3 mass is located at R3 distance, M2 mass is located at R2 distance, and so on and so forth. So Mn mass is located at Rn distance. So if collectively I want to rotate all these particles which are attached, I have to rotate the entire system with respect to z-axis. Z-axis outward. So what will the moment of inertia? I. It will be the summation of all these masses multiplied with the respective distance square. M1 R1 square plus M2 R2 square plus M3 R3 square plus dot Mn Rn square. It is basically the summation of masses with the distance square multiplied equal to 1 to n. So this is the very generalized idea of moment of inertia. That each mass I have to multiply with the distance square, and then I have to take a summation of it, and that will be the moment of inertia with respect to that axis. So here R1, R2, R3 Rn, those are respective distances of M1, M2, M3, Mn from the axis of rotation. This is the axis, this is the distance. That's it. Now I have to find the moment of inertia of this rod. Moment of inertia, MOI, of rod. Now rod mass is capital M and the rod length is L. Now see, this is not a discrete system. This is a continuous system. So this point, the extreme end of one rod is located at L distance. This point, which is very close to the pivot point or the axis of rotation, that point is at 0 distance from the center. So that distance is 0. The middle point, there is some small mass if you consider, that is at L by 2 distance from the center of rotation. So you have to take all this summation, all this mass multiplied by distance square, and you have to take a summation of that. How to do that? So let's say this is the rod of length and this is the x-axis. At x distance, see, distance is variable. Each and every part of this rod is having different distance. So what you have to do? You have to do the summation of that small mass you have to take, and you have to multiply the distance square respectively, and you have to take summation. So x distance, you imagine a small distance of dx. That mass is located at x distance from the center of the rotation. So what is the mass of this small part, dx length? See, L length, the mass is capital M. If it is uniform rod, then dx length, the mass will be m by L into dx. Small mass, dm, is m by L into dx. Now, forget other parts. Only this dm mass, only the dm mass right now is located at distance x from the axis of rotation. What is the moment of inertia of this dm mass? Dm into x square, because x is the distance from the center of the rotation. That is a small moment of inertia di, because dm mass will constitute a small moment of inertia di. Now, if you take summation of that, summation means integration. Integration is also a extensive way of using the summation. So due to the small mass m, the moment of inertia, small moment of inertia di is dm into x square. Now if you add the small masses on the rod, starting from this x equal to 0 and you end at x equal to L, you take a summation of that. Then summation means you have to do integration. Then only you will be able to find out the entire moment of inertia of the one rod. Now let us do the summation means integration. From x equal to 0 to x equal to L. Now let us do it. Now dm, you know, dm is m by L into dx. So we have to express all the variable term in the integration in terms of dx. So see, we can replace the dm with dx, and x square was already there, so x square from 0 to L. Now m by L is constant for a particular rod, it will come outside of the integration, and it will be just integration of x square dx from 0 to L. The integration of x square dx is x cube by 3. So m by L into x cube by 3, limit will be from 0 to L. So it is ml cube by 3L. So it is becoming ml square by 3. So see, the moment of inertia of a rod of mass m, if it is attached to one extreme end, the moment of inertia Iz is ml square by 3. And see the dimension, kg into meter square. I hope you understood. And next lecture we will find out the moment of inertia of a rod if it is pivoted at the middle point.